So, hello everyone. My name is Mahima, a BTech final year student from RGKT Newsweek, specializing in electronics and communication engineering. Today, I am going to present my internship project at Emertxe titled Automatic Washing Machine Simulation using PICSimLab. This project helped me apply core embedded concepts in a practical simulated environment. So, moving on to table of contents. In this presentation, I'll walk you through the key concepts I learned, including embedded C, microcontroller architecture, communication protocols, and the tools I used. I'll also explain the project overview, its working principle, key code snippets, challenges faced, and my final learnings and conclusion. So moving ahead, so what I learned from this during this internship. So during my internship, I gained hands-on experience in embedded C programming, working with the PIC16F877A Microcontroller and simulating circuits using PICSimLab. I learned how to implement I2C and UART protocols, manage timers and interrupts, and build a real-time application, the automatic washing machine simulation. So I worked with this PICSimLab, MPLAB XIDE, and then this is the PIC16F877A microcontroller. So let's take a look at Introduction to Embedded C. So embedded C is a specialized version of C used to program microcontrollers. It provides low-level access to hardware registers and input or output ports. This makes it ideal for bare metal embedded systems with no operating system. Popular compilers include XC8 for PIC. We are also using this XC8 compiler in this automatic washing machine, and Keil for 8051 and GCC for ARM. We can see in this right side corner embedded C programming block diagram, and then we can see the differences between C and embedded C. So C is a straightforward language that is simple to read and edit, and the embedded C language is difficult to read and change, making it difficult to use. So when C is used to fix bugs in C language programs is simple. A software written in embedded C is challenging to bug fix. So when used, the C programming language also supports various other programming languages. Only the processor that the application needs is supported by embedded C. Other programming languages are not supported. And then moving on, we can see the key embedded C concepts. So some core concepts I use include data types, bitwise operators, and control structures like if, while, and switch. I work directly with hardware registers like port B, twist B to control outputs like LEDs. And then pointers are also used to access specific memory locations. You can able to see in this left side corner, this is the block diagram of embedded systems. So yeah. And next we're going to see the basic embedded C code to blink LEDs. So this is a simple code to blink LEDs connected to port B. It shows how to configure port direction using twist B and toggle outputs using port B. So delays are created using __delay_ms for real-time control. And then we can see the features of embedded systems. That is, the embedded system is highly stable, time specific, and it's also task specific, low cost, minimal interface, easy operation, real time, applications like highly efficiency, reliable, and we can have limited memory, less power, and then fault tolerance. We can able to see the clear-cut explanation of this blinking LED code here. Now I'd like to discuss about the microcontrollers overview. So a microcontroller is like a mini computer on a chip. So it contains a CPU, RAM, flash memory, input or output ports, and peripherals like timers and ADCs. So compared to microprocessors, microcontrollers are compact, low cost, and ideal for embedded systems. We can able to see the popular microcontroller families over here. 8051, which is a classic 8-bit MCU, still widely taught. And then AVR used in Arduino boards at Mega 328. And then PIC used in education and industry, as we are also using this PIC16F877A. And then ARM Cortex-M, which is a 32-bit powerful low power, widely used in IoT. And then we can able to see in this right side corner the differences between microcontroller and microprocessor. The purpose of this microcontroller is it's like specific task. It will do a specific task. And then for microprocessor, it's like a general purpose computing. The components in this microcontroller are CPU, RAM, input or output peripherals. Microprocessor is like only CPU. The cost of microcontroller is very low, and then microprocessor is somewhat higher than the microcontroller. And then the design and all these examples we can able to see here. And then next we will see the PIC16F877A architecture and peripherals. So the PIC16F877A is an 8-bit microcontroller from Microchip. It follows hardware architecture, uses a RISC instruction set and runs at up to 20 MHz. It has 5 input or output ports, 3 timers, 10-bit ADC, and then EEPROM, and communication interfaces like UART, I2C, and SPI. You can see the clear-cut explanation about these communication interfaces. And then we can able to see the key features of this PIC16F877A. Moving ahead, serial communication peripherals. So universal synchronous asynchronous receiver transmitter, and then inter-integrated circuit, that's I2C, and serial peripheral interfaces, that's SPI, and pulse width modulation via CCP, that's PWM, and special function registers. We can able to see the clear-cut explanation over here. We are using TISB, port B, and timers, timer 1, 0, 0, 1 and 2 in this special function registers. And then moving ahead, we can able to see about communication protocols in embedded systems. So in embedded systems, protocols like I2C and UART are used to exchange data between microcontrollers and external devices. That is exchange data between microcontrollers and external devices. So I2C uses 2 wires, that's SDA, which is nothing but serial data line. We can see in this overview of this I2C. And SCL, which is nothing but serial clock line. So the key features of this I2C is like it's multi-master, multi-slave support, and it responds accordingly to slaves, and then each device has a unique 7-bit or 10-bit address. So we can able to see the applications of I2C, which is used to connect multiple devices with only 2 lines. And then UART, which is nothing but universal asynchronous receiver transmitter. So it also uses 2 wires. They are transmit and receive, TX, RX. The key features of this UART is like it's a point-to-point communication, 1 transmitter, 1 receiver. Simple to use and implement. Widely used for debugging, PC communication and GSM modules. Requires setting of baud rate, which is nothing but data transfer speed. And then applications of UART like debug logging, and then communication between microcontroller and PC via USB, we can see in our laptops, like and then serial terminals like QCOM. And then going ahead, we can see the timers and interrupts in PIC. So what are timers? Timers are internal counters in microcontrollers. So timers are essential for generating delays and managing time-based tasks like spin and rinse, which we use in this washing machine project. PIC16F877A supports 3 timers: timer 0, timer 1 and timer 2. Interrupts are moving on ahead. Interrupts allow the microcontroller to respond immediately to specific events asynchronously by pausing the main program and executing an interrupt service routine. So interrupts are like interrupting, okay? And then these interrupts are used to handle events like timer overflow or key presses without constantly pulling in the main loop. Okay, so the key registers in interrupts are intercon, global interrupt enable bit, and peripheral interrupt enable. So moving ahead, tools I used in this internship are, as we see the pictures in earlier slides. So the tools I used here is like MPLAB XIDE. So I use MPLAB XIDE from Microchip to write and compile my embedded C code using the XC8 compiler. It provides project management, register level debugging, and .hex file generation for simulation. So advantages of this MPLAB we can see: it's free, feature rich, and officially supported by Microchip. And it simplifies code building, debugging, and memory viewing. And also I used the PICSimLab. PICSimLab is an open source simulator that replicates PIC microcontroller hardware. So we can use it in our software like that. It allowed me to test my washing machine logic using virtual LEDs, digital keypads, and LCDs without needing real hardware. I loaded the compiled hex file from MPLAB into PICSimLab for real-time simulation. And then we can see a workflow summary: writing code in MPLAB and then compile to .hex. The MPLAB will generate .hex files, and then we are loading the .hex file into this PICSimLab, which is like simulate hardware. So why we are using these tools is like easy to set up and use for embedded development. It supports all features needed for my internship, like timers, GPIO, keypads, and LEDs. That's why I use these two tools in my internship. And then moving ahead, the working project overview, like automatic washing machine simulation. So my project simulates an automatic washing machine that operates in multiple cycles. The user selects a washing mode and water level using keypad switches. Timers manages these wash, rinse, and spin durations. And then the CLCD shows status and remaining time. A buzzer alerts the end of the cycle. There's also a door safety check to pause the system if the door is open. So we will see this demo in the upcoming slides on a video. So yeah, you can now see the demo. I'll explain each and every point here. Let me explain this washing machine function definition.c. So this is the MPLAB XIDE environment. You will see this environment here. I write a code for this washing machine, automatic washing machine. So let me explain all these things to you. So yeah. So now I'm going to explain the core logic file of this project, that is I mentioned in this washing machine function definition.c. So this file contains all the main functionalities of the washing machine simulation, such as program display, water level selection, time management, and run cycle logic. So you'll able to see the headers and global variables here. So that's like include main.h and extern unsigned char reset flag. So at the top I have included main.h, which holds all the function declarations and constants used across the project. So you'll see the new word like extern. The extern keyword is used to access global variables declared in other files. For example, reset flag is a system level status flag. Use it for screen transitions. So moving ahead, this CAR washing machine, I use it for about 12, that is the daily, heavy, delicates, white, stain wash, eco cottons, woolens, bed sheets, wash only, aqua store, and so on. So these are arrays of strings representing the available washing modes. Yeah, these are the washing modes and water levels. You can see the water level here: auto, low, medium, high, max. So, and level are indexes used to keep track of the current selection. Okay, I think you will understand this. And then power on screen. You can see this white power on screen here, which is like a startup animation. This function is used to display a boot up animation on the CLCD when the washing machine is turned on. So it gradually fills the top and bottom rows with blocks and then displays a welcome message. Okay, I think you all got this. And then moving on to this washing program display. So this function is called when the user selects a washing mode using switch 4. Like it handles clearing the screen, updating the current mode, displaying 3 modes at a time on lines like 2, 3 and 4 of the CLCD. You can see the CLCD in PICSimLab. Okay. We also handle circular scrolling by resetting program number after 11. And then we're moving ahead to water level screen. So similar to mode selection, this function allows the user to choose water level settings like previously we see. It scrolls through auto, low, medium, high and max, updating the display accordingly. Okay. Moving ahead, we can see the run program, which is like a main execution logic. This is the core function that executes the washing program once started. Let me explain its key responsibilities to you. First, it checks the door status using door status check. Okay. If reset flag indicates start screen, it displays the selected mode and countdown timer. It calculates total time and splits it into wash, rinse and spin using percentages. Then it starts timer 2, which is nothing but TMR2 on is equals to 1, and turns the fan on. Yeah. You can see this wash time, rinse time and spin time over here. I declared all this here and I used this delay also. Okay. So when switch 6 is pressed, the program pauses the timer and stops the fan. Okay. Switching to pause mode. It also updates the current function label like wash, rinse, spin based on the time remaining. Finally, when the timer hits 0, the machine stops, buzzes and displays the program completed message. And then moving ahead to set time. So it's like a dynamic timing logic. This function dynamically sets the wash time based on both the selected program and water level. It uses nested switch cases and assigns values to minutes and seconds. For example, if you select daily and low water level, it sets 33 seconds. Okay, I think you got it. And then I use all these switch cases for all the 12 modes of things like dry only, aqua store and all this. Moving on to door status check. So it's like a safety feature. So this function is an important safety mechanism. It checks if the door is open using RB0 pin. We'll see that all these things in PICSimLab. So if the door is open, the fan and the timer stop. A buzzer sounds like buzzer beeps. A warning is displayed. It resumes operation only after the door is closed properly. It's like our daily washing machine like only. And then at last, clear screen like for the CLCD utility. So this is a helper function that clears the entire CLCD display. I think you see over here. It sends a command to the LCD using CLCD write in instruction mode and waits briefly. So we can now see the main.h, or let me keep this main.c file. Okay. So yeah, let me explain this to you so that you will get a clear. So this is the main file of my washing machine simulation project named main.c. It contains the main function that initializes the system, waits for user input and controls the application flow using a finite state machine based on the current operational mode. Okay, you can see the operational mode over here. So the hash include main.h. This includes the project's master's header file main.h, which contains all global definitions, macros like switch names like switch 5, switch 6 and function prototypes and used across the files. And then hash pragma config wdte is equals to off. This line disables the watchdog timer, which would otherwise reset the microcontroller if the program hangs. Since we are simulating the washing machine and managing timers manually, we don't need this feature. That's why I turned off this. Okay, and then global variables. Unsigned char operational mode is equals to this, and unsigned char reset is equals to reset wash program screen. So operational mode controls which screen or mode is currently active, like washing program selection, water level, start or stop, etc. Reset flag is used to trigger display, that's resets or screen transitions. And then we can see the system initialization over here in this static void. This function initializes all required hardware modules. CLCD for displaying output, digital keypad to read user inputs, Timer2 for timing control. It also enables global and peripheral interrupts as we discussed in timers and interrupts section, and configures the buzzer and fan ports as output by setting their DDRs to 0 and initializing them to off. And then moving ahead to main function, that's program logic. So this is the entry point of the this is the entry point of the program where everything starts. Okay, so welcome screen and wait for switch file. So this CLCD, the system starts by showing a welcome message, this and waits for the user to press switch file to power on the washing machine. And then a small delay loop is added after the button press to avoid switch bouncing effects. So by adding this delay loops, we'll not see any bouncing effects. Okay, and then power on animation. So after pressing switch 5, the screen is cleared and a power on animation is displayed using the power on screen. You can able to see here, giving it a real appliance feel. And then infinite while loop, which is like a system state machine. So while of 1, which is nothing but infinite while loop. So the main logic is enclosed in an infinite loop. It constantly reads the keypad input and decides what to do based on the current operational mode. So next, moving ahead, we can see the mode transitions based on switch 4. So yeah, we'll see here in this. So long pressing switch 4, which is nothing but LP is nothing but long press. So long pressing switch 4 moves the system from washing mode selection, which is nothing but water level screen, start or stop screen. We write everything here in detail. When the start or stop screen is reached, the set time function is called to calculate the washing time based on the selected mode and water level. And then else if statement here, coming over here. So if the system is in pause mode and the user presses switch 5 again, it resumes the wash by turning the timer and fan back on. Okay, I think you will able to get it. So and then I use this all these things, and then let me open the main.h file to let you know what macros I use it and all the stuff. Okay, so wait, let me first show you the CLCD.h where I declare all the things. So CLCD.h is like the header file for the character LCD. CLCD is nothing but character LCD driver. It contains the macros, as I earlier said, and the pin mappings and function declarations required to interface a 16:2 or 16:4, which is nothing but alphanumeric LCD with the PIC16F877A Microcontroller. Okay, so the actual implementation of these functions is written in CLCD.c. We'll see that, which I'll explain after this. Okay, at first this one. So hash define extol frequency like that, which is nothing but this. This defines the crystal oscillator frequency as 20 MHz. This is required for generating accurate delays using built-in delay functions, like as is earlier said, like underscore delay underscore ms and underscore microseconds or milliseconds. We can use that. Okay, and then these are all from here to here. Okay, So these lines define from here to here. These lines define the LCD is physically connected to the microcontroller. The data lines, which are nothing but D0 to D7. Now the data lines are connected to port D. Okay. RS, which is nothing but register select, is connected to pin RE2. Enable, which is nothing but is connected to pin RE1. You can see all this stuff, connections, all these things. So the underscore DDR here. The underscore DDR macros refer to the TRIS registers which are used to configure the pin direction, input or output. The others refer to the actual input or output ports used to send data or control signals to the LCD. And then we can see the command modes, that's instruction or data, which is not inst mode, which is not instruction, data mode. So these define whether we are sending an instruction or data to the LCD. For example, inst mode is used for commands like clear screen. Data mode is used to send characters like A, B, etc. I think you all got it. And then logic levels. These are all logic levels. Simple definitions for high and low logic levels. These improve code readability when setting or clearing control pins. And then we will see the LCD address macros. These are all LCD address macros. So these macros simplify writing data to specific positions on the LCD. So line 1 of 0 sets cursor to start of first row. Line 2 of 5 moves to second row. So 6th character and so on. That's like we'll see this in clear about in CLCD.C. So these memory addresses standard for LCD controllers like HD44780 used in most alphanumeric LCDs. We'll see that in PICSimLab. And then common LCD commands like this. These are all hash defined 8-bit mode to block. These are all the common LCD commands. So these are all predefined instruction codes sent to LCD. So 8-bit mode and 2 lines. These are configure display settings. This clear screen will clears the screen, and then dispawn and cursor off turns the turns the display on without the blinking cursor. And then block is used for animation. It's a full black pixel character, ASCII 255. That's why I write this. And then some of the function declarations are here. These are all the function declarations for controlling the CLCD. Okay. Init CLCD setups the LCD in 8-bit mode. CLCD put CH, which is very important to know. And then which is like places single character at a specified position, which is like single character only. This is for single character, put CH. And then CLCD print, which is like prints a full string to a given line and column. Okay, I think all of you are understanding the code. And then CLCD write, which is like sends a byte as either data or instruction, depending on the mode. So in some like CLCD.h acts like a bridge between our program and the LCD hardware. It abstracts the LCD control logic using macros and function declarations, so making it easy to print messages and status updates in the washing machine project. Now I'd like to explain CLCD.C. So why I explain all these things is like these codes are really important to build any real-time systems, like not only washing machine, we can also build like automatic teller machines and micro ovens, all this related stuff. So for all these things, these codes are really necessary. That's why I'm explaining each and every point in detail. I think you are all understanding. So let me explain the CLCD. Up to now I explain what like washing machine function definition.c and then main.c and CLCD.h, and now I'll explain the CLCD.c. I think you're all aware. Like this file CLCD.c implements all the functions we declared in the CLCD.h header. So it provides low-level control over the character LCD display, including initialization, writing single characters, and printing full strings. So moving on to void CLCD write and these stuff up to here, from here to here. So this is the core function that sends a byte to the LCD. Okay, I think all of you are getting this. So if sets the RS pin, if RS pin is set, writes the data to port D. Okay. So and toggles the enable pin high and then low to latch the data into the LCD. Okay. Finally, there is a delay to let the LCD process the data without any bouncing effects. So the delay is for not getting any bouncing effects. So and then init display controller. So there are so many stuff here. This function runs the standard startup sequence required by most character LCDs. Okay. So it waits for the LCD to power up. It sends the 8-bit initialization command 3 times. Configures the LCD for 2-line display and 5:8 font. And then clears the screen. Turns the display on with the cursor off. So these steps follow the LCD datasheet's initialization sequence. So moving ahead, I'd like to explain this init CLCD. So this function prepares the LCD data and control lines for use. So sets port D as output, sets RE2, which is nothing but I like all the comments here also. Sets RE2, which is nothing but RS, and RE1 enable as output. Then calls initial display controller to start the LCD in the write mode. And then CLCD put CH. This function, as I earlier said in the CLCD.h, put CH and print. This function displays a single character. This put CH displays a single character only. So on the LCD at a given address location, address which is nothing but location. First it sets the cursor using address like line 2 of 5. Then it writes the actual character using data mode. Okay. This is useful in updating timer values or status indicators dynamically. And then I'd like to explain the put CLCD print. This function prints a full string starting at a specified position on the LCD. It first positions the cursor using the address, then it writes each character in the string one by one using a loop. For example, it's used in CLCD print of washing program like that. So to display washing program on the first line of the screen. Yeah. So moving on to okay. I'd like to explain the init timer2, which is nothing but timers. So init timer2 is used to initialize timer2 on the PIC16F877A microcontroller. So this timer plays a crucial role in my project. Like it generates a 1-second interrupts to control the countdown of washing, rinsing and spinning durations in real time. Okay, this include xc.h. This line includes the header for the PIC register definitions. So allowing us to directly access control bits like PR2, Timer2 IE and TMR2 on, which we used in this .h. And then this PR2 250, TMR2 IE1, TMR2 on is equals to 0. So this PR2 250, which is nothing but it sets the period register 2, which is PR, which is nothing but period register 2, which defines the timer overflow interval. The value 250 is selected to match a timing configuration. It contributes to generating 1-second interrupts in the ISR, which is nothing but interrupt service routine. So timer2 IE is equals to 1, which is nothing but this enables the timer to interrupt. It allows the microcontroller to jump to the interrupt service routine. In ISR.c, we will see that when timer2 overflows. So timer2 on is equals to 0, which is nothing but this keeps timer2 off initially, which is timer2 will off initially. We will turn it on only when the washing program starts, typically from run program. We see that in our def.c. So and then moving ahead, we'll see the timers.h file also. Okay. So timers.h is the header file that declares the function used to configure the timer peripheral, specifically timer2 in the project. So let's break it down and I'll explain. This is these 2 lines. This is a standard header guard. It ensures the contents of this file are included only once during compilation, avoiding redefinition errors. Okay, I think you all understanding. And then this void init timer2 of void. This is a function prototype for init timer2. It tells the compiler that the function is defined elsewhere. In this case, in the timers.c file, we'll see that. Already see that. This function setups the timer2 module, use it for real-time countdown logic in the washing machine simulation. And then this end if this closes the header guard, marking the end of the file. So now let me now explain the isr.c. Okay. So yeah. So isr.c contains the interrupt service routine or ISR for timer 2 of the PIC16F877A microcontroller. So the ISR is triggered automatically every time timer 2 overflows. So this allows the washing machine simulation to decrement the wash time precisely once every second without using delays. I think you're understanding. This includes xc.h, includes the xc compiler header, which gives access to all register names and interrupt configuration bits for the PIC. And we use this, already explained this extern. So these variables are declared as extern because they are defined in another file, likely washing machine function definition.c. So they represents the current countdown time remaining in minutes and seconds, as I use the seconds and minutes only. So and then the function declaration. This is like a function declaration. Okay. So this is the interrupt handler. It is automatically called when any enabled interrupt occurs. In this case, this timer 2. So now timer 2 handling. So a static variable. Yeah, this line. So a static variable count is used to accumulate ticks. Timer 2 IF is the timer 2 interrupt flag. It becomes 1 when timer 2 overflows. So if we check this flag to ensure the interrupt was triggered by timer 2. And then second tick generation, all these things. So this line. So every timer 2 overflow happens much faster than 1 second. We accumulate 20,000 overflows to approximate 1 second. So and then the clearing the interrupt flag. Okay, this like clearing interrupt flag. After handling the interrupt, we must clear the timer 2 interrupt flag. Otherwise, the ISR would keep getting called repeatedly. Okay. Okay. So now let me build this project. Like I already built this. So let me open the PICSimLab. This is the environment of the PICSimLab. So I am using this HD4478016x4. I already built the hex file, and I'd like to load this in this PICSimLab. Okay. So yeah. Now I will show you the working simulation of my automatic washing machine project using PICSimLab, which is like a virtual PIC microcontroller simulator. So here I used this PICGenios board here, and I used the PIC16F877A. So the PICGenios board here, which provides built-in support for LCD, display, keypad, switches, LEDs, buzzers and fans, all of which I used in my project. So I'd like to explain each and every part here, and then I'll move ahead with the simulation. So this is a CLCD display. This is like here you'll see. You can see the 16:4. We can also see the 16:2. So for displaying more number of characters, 16, which is nothing but 16 number of characters are present within a line. And then there are 4 rows, like 16 columns and 4 rows, like that, 16:4. So this is where all the user interface messages are displayed, such as like welcome message, mode and water level selection, remaining wash time, function in progress like wash, rinse, spin, and the program completion message. We can able to see the switches over here, bottom of the board, like these are all the switches. So these 3 are also switches. So in this RB0 is acting like switch 1. From 0, 1, 2, 3, 4, 5, 6, 7, 8, 0, 1, 2, 3, 4, 5, 6. These are all we are using in this project. So we have 8 switches labeled from switch 0 to switch 7. Okay. The switch 4, which is nothing but 1, 2, 3, 4. This was the switch 4. is used to scroll through options like modes, levels. Switch 5 is used to start the washing machine. Switch 6 is used to pause or stop the process in our project only. So the RB0, which you'll see here. So the RB0 switches on the side simulates the door status sensor. Okay. And then you'll able to see the LEDs right side of the board. Yeah, here. So these I have used this to represent the internal status lights of the washing machine, like process running, fan on, error or alert, like that. And this is the fan. The fan output is connected to a virtual fan icon on the board. So it turns on when the washing process starts and turns off when the machine is paused or stopped. It also switches off if the door is opened in between the cycle. And then you will able to see the buzzer here. The door, which is like, it's like buzzer indicator flash on when and only when the door is open. And the washing program finishes, it mimics real world feedback for the user. So now I'd like to run the simulation. Let's start the simulation. First you'll able to see once I loaded this hex file, you'll able to see the press key 5 to power on washing machine. Now I'd like to press the key 5. So when I press the key 5, you will see the powering on washing machine in this CLCD screen display. Now we can see the washing program. So there are, as I earlier said, I included 12 modes like daily. So this here there is a star which indicates like that's the mode we selected. So once I press the switch 4, we can able to see it's like heavy and then delicates, whites, stain wash, eco cottons, woolens, bed sheets, rinse plus dry, dry only, wash only, aqua store, and then coming again daily, heavy. Now I'd like to put delicates, or else I'd like to put stain wash. Okay, so when I long press it in the stain wash, on that stain wash, we'll able to see the water level, which is like we'll see the water levels like auto, medium, auto, low, medium, high, max. Now I'd like to put the auto status only. So once I long pressed in this RB3, which is nothing but switch 4, so it's asking like press switch. So when we press switch 5, it will start working, like the washing machine gets started. It will start, and then when we press switch 6, it will stop. Okay, are you interested to see the output? Let's dive into that. So I am going to press the switch 5. Yeah, it shows program. I started the stain wash, that's why it shows like, yeah, stain wash. And then time is for stain wash, it's like 1 minute 36 seconds. Oh, so when 5 is nothing but start, 6 is nothing but pause. I'd like to press the switch 6 to let you know like it's pausing or not. Switch 6 is nothing but pressing RB5. So I'm pressing RB5. Yeah, it's really working. Like it shows the pause. Yeah, pause. It's paused. Okay, now I'd like to press switch 5 and it will start again, and it will resume from where it ended. Okay. Yeah, I can able to see like it's resuming from where it's ended. Once I press this RB0, so door is open, please close door, it shows. So I'd like to resume this. Okay. So it's like again resuming from where it's ended. The door is open, please close door. And the buzzer is like on, and the fan is like not off. Okay. And then it's resuming where it ended. Okay. When I'm just let you know, that's why I'm doing it again and again. Okay. So once I press switch 5 to start the wash, the system now enters start mode, and you'll see the current program name, timer countdown, the current stage, whether it's wash, rinse or spin. So here it shows like rinse. Up to now it shows wash. Now it shows rinse. and then after some time it will show spin. Please carefully observe the changes, like what function it's running on. So once it's like ended, the time is ended, it will show like program is ended, take your clothes, and it will just beep sound, the buzzer will beep again. Once watch this, once the timer reaches to 00 to 00, the mission completes the cycle. The fan will stop and the buzzer beeps. Observe the changes carefully and the message program completed, remove clothes is shown. Okay, I think you all are able to understand this. So this simulation demonstrates a fully functional real-time embedded system using only a microcontroller, LCD, digital inputs and timers. So now I'd like to okay. So up to now we'll see the demo. So project overview and all this stuff, and I'll put some key code snippets over here. You can able to see them. Okay, so I'd like to what challenges I faced is managing multi-file modular code, and I also faced some challenges like handling user inputs via keypad, and then also faced like simulating real-time behavior in PICSimLab and debugging logical bugs and all this stuff. So PICSimLab didn't behave exactly like hardware, but visualizing hardware behavior like LED blinking and fan response demanding accurate timing. Okay, the key learnings from this project are: it builds a strong foundation in my embedded C, and I gained confidence in writing efficient and modular embedded C code. So, and I also learned like real-time system design, and I also learned something like microcontroller interfacing, like hands-on experience with input or output ports, timers and CLCDs, keypads and safety logic, and the importance of code modularity. And then also learned the simulation and testing skills, like became comfortable with using PICSimLab as a real hardware substitute, understood how to simulate, test and validate MCU based systems without physical boards. So conclusion, before concluding, I'd like to express my sincere gratitude to Emertxe for providing me this wonderful opportunity so to explore and work on real-time embedded systems. This internship has truly helped me enhance my practical skills and bridge the gap between theory and application. And I'd like to thank a special thanks to my mentors, Anusha ma'am for explaining the embedded C, and then Guhapriya ma'am for this microcontrollers and all the related stuff, and then this project implementation for their constant support and guidance and encouragement throughout this project. So your feedback and mentorship have been invaluable in helping me complete this project with confidence, ma'am. My heartfelt thanks also goes to the entire Emertxe team, the heads and the leadership, for building such an enriching and supportive learning environment. Thank you once again to everyone who supported me in making this project a success. Thank you one and all.